And there's a lot of confusion about what that actually means. Here we go. But this is how we're going to go about it. We're going to talk about systems engineering and some of the historical aspects of systems engineering. We're going to talk about its evolution, the complexity, which some of you are not aware of because you're not my age. And we'll be talking about systems engineering at CSU, and we'll just have a quick summary at the end. So Dan and I are going to trade off doing some of this. Okay. And so the birth of systems engineering. Formal engineering really started as far as a quote systems engineering with the Bell Labs back in the 1940s when they were doing some missile work and some other kinds of things. The first formally applied systems engineer was supposed to be the Manhattan Project, which most of you know is the project that was used to build the U.S. atomic bomb. And then everybody actually started using it. It had been started using in the UK, and the UK is quite good at this. Can you not hear me?
It says a little bit muffled, so I was trying to adjust this. You're good.
See if that works. Are you listening? Or is somebody else listening?
They said it's much better now.
Much better now. Okay, it's closer to me. Okay, great. So anyway, I wish there was a screen that got in that would be easier. A lot of people actually use systems engineering now. Let's go to the next one. I'm gonna work that way.
I just clicked it. Yep.
Okay.
Just let me know and I'll.
So if you actually go back to 5,000 years BC, the Egyptians used significant amount of systems engineering. And they really realized that the workers they had were also part of the system that they were using to build all these pyramids. And it took them a long time. They had documentation. They knew exactly what they were supposed to do. They knew how to manage their resources. So they also used program management along with systems engineering to build these things. And some of the ways they did it are quite fascinating. And then in the 1200s, you can see the Great Wall of China was also using program management and systems engineering. 1750, they started trying to apply types of systems engineering to building boats. Now, it worked pretty well until the people that were actually funding the boats that had to be most of the kings wanted some certain things of their own, and they would make requirements change at the very last minute. That's what happened to the Vasa, and ended up on its maiden voyage actually sinking because the king changed requirements so many times it was a problem. But you can see we're going on into railway transportation, and we end up obviously in the 1980s. And coming up with some systems that are certainly not as mechanically simple, right? So we start getting into a different age of what's actually happening. Oops. So here we have actually some of the things that started happening. So you can see that we started having embedded software and different kinds of control systems in the systems that we were building, particularly for the military. Now, the military has been using this for a long time, systems engineering. I would say that a lot of manufacturing plants and people that were doing development also use systems engineering. But you can see power generation, we're talking about fuel cells, electric warships was something that we've actually tried. Electric aircraft and propulsion is going to be something that becomes bigger and bigger, particularly as we are trying to get away from fossil fuels. We have space-based radar. So we have a number of these systems that are infinitely more complex than anything that we had had before. So we can do ways of actually going about trying to capture how we're doing it and actually be able to do it faster. Because if you do it all with looking at documents and you do it in a serial process, then have a little bit of a problem, and that's time and money. So these are some of the examples when we started really getting into some really complex things. Of course, space is always one of our most complex because it's a context that we as humans can't really associate with. When you're in space, everything is different and all the requirements are different. And the way we go about now doing systems engineering at NASA is quite different than the way NASA started out doing systems engineering. But these are some of the early ones that you can see that some of the technologies were actually being tried out in the early 2000s and late 1990s, where we actually put satellites up and we put small satellites up, and we actually had to have them systematically talk to a lot of other things. And this became even more complicated. Okay, and here's the tactical satellites. These actually were in 2006, I believe. This is one of Rod Sega's slides, and he was actually talking about some of the first tactical satellites on orbit. And this is really important because this made everything, again, in the Defense Department change. And when things in the Defense Department changes, it almost always flows down to dual use technology, which means if it happens with the defense people first, at that point in time, it would then become part of what we would consider our culture. Now, frankly, in my opinion, it's going the other way around. So all the things that are happening now are actually going to be used for some sort of defense thing, but it's going to go through a commercial first. It's going to go through our culture first. We've got, I just had a student that did his master's project on actually being the Unreal Engine, using it to do some of the digital engineering, the modeling and simulation, because he does it in his job and he knows how complicated and complex and onerous it is to try to introduce a new system capability. So he decided that he was going to use Unreal Engine and see if he could do the same thing with it, but do it quicker and faster and actually have a lot more capability, which, I don't know how much you know about Unreal Engine, but it's a gaming program for modeling and simulation, basically. And he used it to improve the work he does with radars and being able to lock on and track radars. He's actually used it to improve that. So now he's going to take what he learned from that with a commercial product and fix some of the things that they have problems with in his work, which I thought was a really clever idea. Yes, sir.
We're doing the same thing with the gaming engine called Carla to simulate
good.
automotive trajectories and so forth.
Good. Well,
Yeah.
I think there's a real market for this. I think it is so much easier, you know, and some of this stuff is using brand new technology, the old modeling and simulation. And honestly, the old modeling and simulation is one of the reasons why a lot of, we split these, or I heard a lecture on this where we split systems engineers into 3 categories. We have digital natives, which are the young people now, right? We have digital adapters. I would be a digital adapter kind of person, right? And then we have the digital resistant ones. And I don't think we have anybody in this room that's digital resistant, although they're the ones that should be here.
I have some family members.
Yeah, I do too. I have some old colleagues that are definitely digital resistant. Yes, Steve.
I just for clarity, I'm trying to understand the gaming engine. Is that like the simulation engine? that
Yeah.
presents
modeling
it?
and
No,
simulation.
like I use Minecraft, for example, when the students look at.
That's a modeling and simulation.
Well,
engine.
is that a similar concept or is it just a?
It's a little bit different. Minecraft is a little bit
Or like the
more
environment?
fundamental than, or at least it was when I played it with my grandson. So he was a big Minecraft buff, and his mother wanted me to talk in not during Minecraft, got to do modeling and simulation, and he's going to need to know how to do it. I mean, he was 8 years old when he did it. But it was a great addition. He's now, well, I thought it was a great addition. But I thought it was, and it has really paid off for him because he's doing rendering now as a college senior for a major company in the United States in part-time. And he's really good at it. So I'll get back to this. So we had all these different things that we were trying to pull together. And you can see that we had some capabilities here. These are pretty impressive capabilities on their own. But one of the things that we lacked, even in 2006, was a really good way of going back and repeating what we had already done. Because even in 2006, a good portion of our documentation was already in digital documents. That was a good thing, instead of just paper documents. But you still had to go back through everything to find what you wanted. You couldn't really understand how you wanted to go about it because you're still looking at paper. Now, there's a certain part of our brain that is actually wired to remember pictures better. We have a thing called pictorial superiority. And that means that a different part of our brain is processing a picture than it does a table or a bunch of written words. And you can actually recall the picture much quicker and much better in more detail than you can the written language. So after this, they go back to this and then they decide they're going to do some of these things over and over because you have success the first time. And then you find out maybe you don't have as much success the second time. And then you start to realize that you're doing the same things over and over and over again that have already been done. Now, this has been going on for a long time. When I used to work on a lot of defense projects, I would find things that going back in the literature that we were trying to do again, even though it had been done 20 years before. And now I still see the same thing. I see a lot of people trying to do things and finding out the same information that we did 20 years before, because it was all primarily documented in papers and things like that, and not accessible to everyone. So 21st century and beyond, I'm sure, we're looking at the technology changing dramatically and very, very fast. And not just the US technology, it's going to be everywhere, right? We've got more complexity in aerospace and anything that we have on Earth than we've ever had before. And we're trying to use the same tools to work with it, and it becomes a little more difficult. That's why you're going to a gaming program for that, the same reason why you went to Unreal Engine. The data required to model things sometimes can be onerous as well. So we have more data than we've ever had. We have probably data overload in many areas. We are looking at trying to find ways of actionable data, because the actionable data is really what we want, not just more data. And then we have cost optimization and affordability. That becomes ever so much more important, particularly since we're now, as a country, competing on a global market rather than just being at the forefront of everything. So, systems approaches, they've got to change, right? We have more integration into more systems. We have systems of systems. We have ways that we never believed that systems would even be able to interconnect and interact with each other. So we start doing things called digital twin, model-based systems engineering, which all brings us to digital engineering. And these evolving technologies that we have and we need to be able to keep together are the adaptive manufacturing, adaptive and additive. Those are two different things, but very similar, because adaptive manufacturing is when you can actually change things out, and there's artificial intelligence built in the manufacturing part of it, and it can actually adapt to whatever product you're trying to make. Additive manufacturing, I think a lot of you know what we're doing with that. We've got 3D printing of metals and all kinds of other things. It's really fascinating, but then again, when we do that, we have to feed a model into a printer, a 3D printer, right? And getting that model is still, and keeping that model is something that is really part of that digital thread. And now we have cybersecurity and challenges, because this is, you have all this digital data, you can get at it because of the way it's stored typically, or the form that it's in, and they can use that. That's something that's a little bit different than being able to take a document and then figure out what people are doing from it. It takes more time. You can actually get the model, then you can do something with it pretty rapidly. So it makes it even more at risk as far as cybersecurity goes. So the DoD, along with everybody else, let's say there's a group of federal contractors, I'd say, because that really is where most of this is used, or has been used. But the DoD realized that a lot of things were changing, and what was changing is that taking 20 years to actually get a product to a soldier is too long. By the time he gets there, it's already obsolete, right? So it's not working well, and we need to change it. So they started something back in 2020, which they want to transform all engineering into digital engineering. And primarily the way they're going to do that is doing it through systems engineering, because typically systems engineering have been the keeper of all the technical information, right? Keeper of all the technical documents. And typically the people who actually knew how to put things together. Back in the 1990s, there started to be a large group of people that were retiring, that were systems engineers. And they identified back in the mid-1990s that there was going to be a real problem, because they didn't have these people anymore. They didn't know how to do these things without these people, right? The documentation is not great. So we have all these legacy systems. And a lot of people that manufacture things are very much like that. I come from a manufacturing background for part of it, and a scientific background. And my job was actually to take things from concept and get it all the way out through the manufacturing plants and everything like that. And I really liked that. But when you go back to find out what people did certain things, there was nothing there to tell us. So we lost a whole lot of information. We lost a lot of technology. We lost a lot of skills. They identified this, but they still didn't hire systems engineering people who come in and fill those jobs, because they couldn't find them, because we weren't teaching them in this country. Now, England was doing a much better job about it. They had caught on to this much before. I worked for BA Systems when they bought our company in the US. And all of a sudden, systems engineering was a really big deal, because they had actually funded a department at the University of Loughborough in England just for systems engineering, and doing it starting at the bachelor level too. So anyway, the DoD decided they were going to do something different. Now they're calling this adaptive acquisition pathway. So it can pick any one of these pathways, depending on what your project is, how complex it is, how much it costs, right? And of course, what its mission is. So when you look at this is a great deal faster than it used to be. We're talking about urgent of 2 years. Urgent used to be, well, I'll be honest with you, we made some urgent things. We actually worked our butt off, and we got it through manufacturing. We'd never made it before, but we got it through manufacturing in 2 weeks. Now, these things that we made didn't even get over to the battlefield, because their logistics were so messed up that they couldn't get it there in time to actually use them. So they realized they've got a big problem. They decided they're going to do something about it. 2 years, 5 years, 1 year down here just for this planning phase. That's for software, so you need to do it really quickly. And then down here, it becomes a little bit more of the regular part of it. But still, that's not 20 years down the road. You know, they're still looking 5 years, 10 years at most. So a lot of things have got to change in order to do this. And cybersecurity is now having to be in every part of this because then again, we're using all this digital information. So we start integrating different things. And this is actually something that came from David Greer, who is OSD, BTRD, there's all kinds of, you know, things you can throw out there to describe her. But anyway, for the Defense Department, she is probably the leading director for systems engineering. And she's talking about modular open systems approach, where we have open architectures, prototyping and experimentation, which we've all done. We've done all of these things. We've done modeling and simulation. That is not new. We've been doing modeling and simulation since partially the 80s, but not the same way that we're doing it now. But some of the tools, unfortunately, for radar and certain systems are still that old. I know some systems that we worked on that we were not allowed, we had to go back and figure out what the 1980s technology was in order to fix some of the things that were still there. And that was really hard because it was all documentation. And people go through and get rid of their documentation after about 7 or 10 years. It doesn't exist anymore. So anyway, we have assessments and analytics. Analytics are going to be a big thing, of course, already are, because we have so much data. And we need to be able to pull actionable data out of it. And then we have, well, everybody knows that Batchelor and all those kinds of things. So in her definition, she has systems engineering in the center of this. And to me, digital engineering probably encompasses everything that's in there, not just its own little block. So transforming systems engineering, two of the things that they're really going to be counting on and focusing on is digital engineering. Everybody's got to go to digital engineering. They want to work with the government, and a modular open systems approach. So this is getting to be really interesting. So you think about it, and particularly those digital resistant people, the first thing they're going to say is, why are we doing this, right? If it ain't broke, don't fix it. I've heard that. It's not, we can do it better. It's just, if it ain't broke, how do we fix it? Okay. So here are some definitions of digital engineering. None of these are perfect. These all come from public sources on how they actually define digital engineering. You'll notice that there is some really interesting parts of it though. It's integrated, it's digital. It goes throughout the whole life cycle. You have a model. You're going to use a model. You're going to store everything in a digital twin. And so I'm just letting you guys read these because you'll see these over and over and over again. But there's some commonalities to every one of these definitions. And trusted sources of data is one of the most favorite things to talk about. And models that are used across that. And that means everybody's going to be sharing the same modeling parts. Yeah.
The notion of trusted source, I think, is challenging.
I do too. That's why I don't usually put it in there because, but go ahead.
Yeah, I was going to ask if there's a consideration on how to actually establish trust and who is the trust bearer, trust keeper in, like, how do we go forward with that idea? So right now the internet uses public key infrastructure, and you have these certificate authorities, and that's how we establish trust.
That's
right
right.
now.
That's right. That's
But
how we do it right now. So how are we going to?
How are we going to do it in the future, and is that model going to be able to include all of these objectives also?
I don't think that's all been worked out yet. I am
Yes, that's why we have a
basically a
job.
distrustful. Unless your model's been validated, you know, I'm pretty distrustful because I know how easy it is to leave things out, right? But we're getting better at modeling, so it should be better. So they are actually considering some of this trusted data, historical data as well. And a lot of it is not in the format that it would need to be for some of that. There's a lot of work to be done out here. Dan's going to get into some of it, so.
Yeah, maybe my comment before we get into those slides is that it should be a consideration in how you connect the different data sources and tools together. So, it can be part of the requirements of your digital thread is that you have some way to authenticate and trust different data sources. So I think it's a part of the picture of how you build up the digital engineering picture rather than, a particularly solved problem at this point.
But you've obviously identified Bill, I'd say.
Opportunity is what
An
it is. It's an opportunity for.
That's right, because if somebody does any changes, something you consider trusted data, then they're in trouble. Okay, let's go to the next one. So digital thread, you've heard digital thread, right? What is a digital thread? It is just this digital framework, and this is the first one, I like this one down here. A communication and data flow framework, where we actually have everything about a product that is kept with it through its entire life cycle. And one of the most important things about this is you actually go through modeling this, even through its life cycle, before you produce it. Yes, this is how you save money. This is how you save time. This is how, once you have gone through a system, you can go back and repeat it. And I'm going to give you a case study that Boeing did on using digital engineering with this. But just think about it. Once you've done something, you have already cut the amount of time that it's going to take for you to do it again. If you have digital thread, every time you go back, you're going to see savings over the first. The first may be 30%, but when you add another 30% reduction in cost and time and improvement in quality, then you're really talking about something that could be transformational when you actually go to produce a lot of things. So in my definition, this is an unbroken link from the original computer model to the final product, and you do it before it actually gets manufactured. So you model the manufacturing. You model how you're going to do everything, and you keep it together. Now, we used to do this anyway, right? We would actually have plans and figure out how we were going to do everything down through the life cycle. They were on paper. Nobody ever paid any attention to them unless you were actually in charge of that particular phase. And things got changed, but doing it ahead of time is going to cost us, but actually save us so much money and so much time and so much cost. And it's going to be easier. And to me, that's one of the big things. It is actually going to be easier for systems engineers to do their job. And that's what I keep trying to preach, and I should use that word, to the digital resistance, because they're used to it. And there is a huge resistance to this in engineers that have been engineers for a long, long time. For whatever reason, it is a cultural thing to some degree. But we've been talking about this. This is happening at Lockheed, it happened at Boeing, it's happening all over the place. So digital twin, that is that repository that's going to store all this information. It's going to have that, so when you start making changes, when you want to update a system, what are you going to do? You're going to go back to your digital twin. You're going to look at what you need to do, right, to be able to make these changes, and you're going to actually be able to do them on yet a copy of the digital twin and be able to figure out how it works, how things need to be integrated before you ever actually have to do it. This is pretty powerful. This is one of the best things. We used to do it by making all of these individual prototypes of everything, which takes a lot of time and a lot of money. It gave us the information that we wanted to. I was really hesitant to actually allow models to give me that information until I realized it was a really good use for them, because I could cut out I don't know, maybe 50% of the stuff we're gonna do by hand. If we use the model and then just using the model, we just pick out the best solutions from that, which gave us a lot to go on. So here again, definitions of that digital twin. And those are things that we're going to be talking about, and it's going to be really important to everything digital engineering as we go. Are there any questions on that?
A digital twin has to include sensors that
How do you
feedback.
select the level of fidelity for your digital?
Well, a good bit of that's going to be what's the fidelity of the model too? Are you saying, how do you select what it needs to be
Right.
versus what it is?
Yeah, so I mean, I'll just say your new Tesla, right? We want a digital twin of it.
Mhm.
Do we actually model the, the cache and the processor that's reading the instructions off the register, right? In that little tiny detail that's so buried in there that if we flip a bit, what happens to the whole system? Or do we treat that like a block and just assume that it's going to execute its jobs correctly?
I think you have to realize that it could affect everything. And Boeing, when they did their T-7A, actually modeled everything. So I think it depends on criticality,
Okay.
right? What happens, like risk, looking at from a risk standpoint, what happens if this has what kind of impact does it have?
Yeah, no, that makes sense. It's a big budget to be able to do
absolutely.
that level.
Yeah, it is, and you have to realize how it's different. If it's not gonna make a lot of difference, or the impact will be small and the probability will be small, chances are you're not gonna do it until you have to. Yes, ma'am.
I just wanted to add on what you're saying. I think the fidelity of the model may also depend on what your needs are. So if you need to model down to that level, then I would expect the model to go to that level. But if you really only need the frame of the car, if you're looking at, maybe human interaction with the frame, then you don't need that level at all. You need the doors, the seats, the door handles, that sort of thing. So looking at metrics, you don't need certain aspects. So I think it really is going to depend on what are you focusing in on and what you're looking for.
But just think about it, if you're in the software development group, then that would be something, if you had a ton of money, you could actually add into the model, right? Or be working to add into the model at some point in time. Because from a really big system standpoint and customer satisfaction, now that you've seen a Tesla car, Jared. Yeah, I can see you could get some really dissatisfied customers if that little glitch were to happen, because you really couldn't go anywhere. Yeah, you can, yeah.
Cameron has a question for you.
Okay.
How is the digital twin different to the multi-physics, multi-fidelity modeling that we use today?
That part fits into the digital twin. Remember, the digital twin is the storage place for it, right? So all of that information goes into the digital twin along with all the systems modeling information. Yeah, tell Cameron your question. I was afraid it was going to be harder though.
So my thoughts on the same line that Cameron's speaking to, and in my realm of water and energy systems, the digital twin is an aspirational goal to have like a genetic representation of the physical system. So yes, it would include, the biological processes that are occurring within the anaerobic digesters and the full thing. So you have like this, it's as if you created and constructed a full representation. So that's where it brings it past kind of the multifactorial analysis models that we particularly looked at, real environments work. Now that kind of conflicts with the whole question about parsimony, is like how, with the parsimonious model only develop what you need to answer your questions, are we wasting our time developing these tools? I don't know, probably going to be
So,
answered over.
I actually think this, I think our systems engineer is probably the one that's going to make those decisions. And there is such a thing now as a digital engineer. I've seen some job descriptions for them, and I want to make sure that we use digital engineers as well.
Feel like the Microsoft paperclip?
No, not at all. Not at all. It's more like Python, it's more like data analytics, it's more like some of the things that. Let's go on to the next one. All right, who else going to be involved in this? So this big transformation into digital engineering, these are all stakeholders. You will notice that academia is one. And there are certain other systems that are out there, professional organizations. Obviously, the government is a big part of this, you know, as industry. And this is the classic systems engineering theme. One of the things that is happening with this transformation of systems engineering is because, you know, everybody got on the digital bandwagon. And we've actually been doing things called rolling wave or iterative projects, where we had these phases that we went through, and we went through these things at the same time, or serially, sometimes parallelly, but we went through a whole lot of these, and this is what we're looking at now. Is going through that and trying to speed up things. That was the real reason why Agile came along to start with, is because you have to speed up development. You could get the customer's feedback almost immediately, and that's key to being able to do it quickly. If you've ever worked with any military things, and you know, sometimes getting their feedback is very difficult, and you may not get it until the very end, which is, I think, starting to change a lot. You force it to change, but you're going to see that you're going to be going through these things quite frequently. It's not just going to be one time that you go through it. It's going to be several times in several periods as you go through the development cycle. Go ahead, I think everybody sees enough. And this is a Mike Murphy slide. I particularly liked it because he saw that we were going to have to do significant amounts of cybersecurity very early on. And that means even at the very beginning, when you think about the concept and you're actually pulling requirements from your stakeholders and everything like that, you're really going to have to make sure that you have cybersecurity at every level that it is. This is proving out to be, I don't know if I could say it, a little more troublesome than I thought it was going to be. It's definitely more complex than they realized it was going to be, particularly since there are smart people every day that are getting smarter about how to hack into systems, and it's just going to keep going that way. This basically is starting with model-based systems engineer, and particularly anchored in the architecture models. You can see that here. So this has requirements in it, requirements allocation at a very high level. Structural diagrams, behavioral diagrams, data models, services, interfaces. That's pretty powerful, and you would have to actually make sure that all this information is secure in a way before it ever gets into any of this. So this is going to be interesting because right now we don't do an extra great job at keeping our requirements secure. Because they're so early, we know they're going to change, therefore they're not as important to protect. That's been historically what we're looking at. Intended outcomes, built-in flexibility. I would not say just speed to the battlefield, but speed to market, speed to services. I think we are looking at, the United States is looking at this as a way to reestablish our technical dominance that we had for many, many years. It's not like that anymore, right? Because there are a lot of countries that are at least as technically advanced as we are in many, many ways. Digitally documented systems, even on legacy systems. So there's a big push to going back to the legacy system and creating digital models for them so they can be used. Carnegie Mellon just ended up doing one from an old legacy system for the Air Force, and had to do it because there was no information, there was no modeling, there was nothing. All they had were aircraft to do it on. Interesting. That's where academia could really play a big part in as well. Secure documentation, communication, and then we believe will be more competitive, right? And I truly believe that once systems engineers particularly realize how much easier this will make their job to get all these things done, that it will actually free up some of their significant brain power to actually innovate more and explore more and figure out things better.
We have 15 minutes left, just so you know.
I don't have it. Do you have it? Do I have that finished?
I think we have-
Oh, okay, I've taken up a lot of time, I'm gonna speed up right here. What does this mean? Big changes. Traditional B is gonna be used on an iterative basis, transition to documentation to digital, automatic generation of reports, and that means all the systems engineering documents that we used to create now will be done automatically. Central depository and that digital thread. It's going to have some changes in attitude and culture within the systems engineering community. I think that's already happening. And then cybersecurity is at all levels. Just to wrap up my little portion, case study, the Boeing T-7A is a great example of this. Go ahead. This happens to be a pilot training plane for the Air Force. It's replacing the T-38 that was used by the Tuskegee Airmen to train on. They are trying to honor and make sure that they have everything in there that they need to actually be able to have pilots actually train effectively in there. So it's a supersonic one, it's 47 feet long. They was built from scratch and designed from scratch using digital engineering. So they really broke the norm when they did this. They used all digital engineering processes, agile software development, open architecture mission systems, so you can actually do development, future aircraft development easier, modular design. They put all the fighter-like performance in that aircraft, which before they've only been able to put partials in. They designed it for maintainability. This is key. For anybody that remembers when they made that first of the new Camaros, and you had to drop the engine to change the spark plugs. You remember that? Yeah, I'm glad there's somebody finally is that remembers that. I had little hands, so I could get in there. It wasn't that bad. But side opening for the canopy, high wings, so that you could actually inspect them easier. Got down door panels. Maintenance control panel and the single point for refueling. Now they're on the same side. That means it's really a lot easier to do and faster. Now, if they need to change out an engine, it takes 4 people and they can do it before lunch. And it has interchangeable parts for the rudders and stabilizers and actuators. Concept to first flight in 36 months, which is phenomenal for an airplane. Absolutely phenomenal. Accelerated the bid times. This is what they saw, a 75% increase improvement in first-time engineering quality. That is dramatic. 80% reduction in assembly hours and a 50% reduction in software development and verification time. And I have 2 little videos that I won't give you because of time, but you're welcome to look at it. It shows that it actually was able to restart itself at 20,000 feet. And that they are now looking to replace it with another one of the other planes, the T-47, the Goshawk, which is the Navy's fighter training. Okay, good.
All right. Take over.
Yep.
Dan Herber, I'm going to talk a little bit more about, some of the techniques, what you need to do digital engineering, or some ideas along this area, because it's a very big open space. So this is potentially redefining how we do many of the engineering practices. So lots of things we do in engineering, Number of them are listed here, big data analytics, data visualization, physics-based models, digital manufacturing, AI, cloud, augmented reality, virtual reality. There's all these different pieces. Some of these are older, approaches or technologies. Some of these are more are newer ones. And we see these as enabling technologies for building a digital engineering kind of approach and building what we'll see on the next slide, that digital thread idea. Here's one example. This is not meant to be, this is what a digital thread is, because what a digital thread is should be reflective of the engineering approaches that your organization or the particular domain that you are exploring is. But in these approaches, we have these often specific roles, whether it's a team of people doing requirements, for example, or system architecture, or at some point there's a split between hardware and software, and then at some point they get merged back together once design's being done. There's often, one person can't do everything. People have their preferred tools. Tools are developed with their own capabilities, with their own ability to do the engineering that we want to do. A lot of what digital engineering entails, a lot of what the digital thread idea entails is how do we better connect these tools? One common approach now is they're connected by us. We communicate our results. We send our results in email and through a report or presentation, or through ad hoc data files, etc. The goal in this enabling the digital thread is how can we better automate this communication between tools, between the data between tools, between the models that represent the things that we're doing in our engineering activity. So the two groups here are tools, many different tools, answer specific questions of the digital engineering needs. Tools often require training the right mindset for effective use. So in some cases, right now I'm focusing not on things like data visualization or virtual reality. Those are ways we have these interoperability with these tools. You can get different perspectives and different ways to interact with traditional approaches to doing some of these engineering activities. So in some cases, it might require you to learn some new tools or understand or at least interpret what you're seeing from these tools. But another major aspect here is the interoperability. So many, you'll see lots of these big tool vendors, I'm listing, a very select few of things here on the slide, are building interoperability between the tools. You'll see on their websites, we can do digital engineering for you. And they're usually enabling that mostly through their own tool suites. But there's also formats and standards. So part of this approach can be if you are developing your data and models in standardized approaches, these tools can sometimes export. So instead of just having interoperability between different tools, you can have interoperability between tools in the same layer. Can I communicate a Cameo Systems modeler with Rational Rhapsody, for example? So there's a lot of work. I've listed some standards here, some architecture requirements, physics modeling. There's XML schemas being developed for specific data standardization, and then even this open services for lifecycle collaboration, which is in particular using web-based protocols to communicate between different tools. It's trying to build a standardized way for many different tools to communicate. So looking at the standards and understanding what are your needs and how, do you want to be stuck with one tool vendor, or do you want to adopt standards so that you can have more data freedom between things, can enable this reuse in the digital thread in the long term. You can realize some of these benefits that Anne was talking about earlier about reuse and those types of things. So next slide, please. So one key aspect here that was already mentioned that I talk about in my courses is the idea of model-based system engineering. How does this perhaps fit into this larger idea of digital engineering? Well, MBSE puts the model at the center of system design and management. So if we look at the left, the idea that there's in the past, we did engineering of a system and there is groups doing their own thing. There's implicit dependencies. Engineering depended on the CAD team analysis, and there were separate teams, but they had to communicate and get information between each other. The model-centric approaches, which model-based system engineering is proposing, is putting instead a system model at the center. And if we think about what we were talking about on the previous slide, having ways for those tools to interact. Now there's a common pathway, there's a single source of truth. There is a source where you can, or there's a point where you can communicate between these tools potentially more effectively. So an MBSE-like approach can help standardize what's in the system so that everyone has a common picture, but also potentially facilitate that communication, that transfer of data and other, pieces of my system definition between these different type of buildings. So single source of truth, single point of access and modification for data system understanding, maybe a little to Jeremy's point of that, how do you trust things? Well, if we have a single source model and that's very well controlled, then this can be seen as, there's not two separate definitions of the system at two different points in our organization. There's a single source for that information. And this still allows and supports discipline-specific views. So even having this single system model, the idea is that generation of artifacts or, someone from software perspective can pull out what they need from that to do their job effectively. They don't need necessarily everything in the model, but they do have access to those additional connections, those additional pathways to understand how the software fits into the bigger picture or similar like questions like that. And this is very tool specific or tool centric idea. There are standards, but standards need to be implemented with tools. So a tool like image system modeling here, for example, helps support the development of these types of models. And it's, many of these are just very tool driven in terms of how do you actually interact in a digital engineering manner. Understanding those tools is part of realizing the digital engineering vision. Next slide, please. So I just want to give one example. Again, there's, you saw how many different potential communication pathways, how many different things you might need to communicate if you have a full digital thread. Certain tools are implementing certain capabilities between existing tools. So one example here is Phoenix Integration ModelCenter, MBSE. So we have this idea of a centralized, MBSE system model. Well, there's multiple tools that can potentially accomplish this. I've listed 4, pretty common ones here. But what if we want to do, more detailed mechanical analysis or some optimization or cost modeling, things like that? Well, perhaps those are in other tools, or there's certain capabilities not available in these MBSE-like tools. Well, to bridge the gap, as they're putting it here, between these different tools, well, they build into the tools a GUI that's on the top right, for example, where import the model and take information. I don't want everything from it. I, for example, want the parametric side, I want the equations, I want the requirements so that I can validate those requirements against my more detailed models that I'm going to use in this tool. So this particular tool is a way to potentially bridge between the MBSE side and your physics-based modeling side and bring them all together. So understanding, again, the tool picture is really important because you have to understand what capabilities are available and how what you want to accomplish fits into that overall picture. And this particular platform even supports the idea of cloud computing. Someone is defining what the capability is, the modeler, if you will, and they make that capability available for the broad organization. So instead of only that modeler having access to the information and being able to do trade studies or exploring or just understanding the system, a certain analyst or someone else who has a different role can potentially access that, and it enables them to have access to data, access to system models that they did not have before, and perhaps leverage cloud computing resources, save on the resources more generally, where you ad hoc allocate things as the needs arise rather than every single person having their own workstation and things like that. So this type of picture is a digital engineering picture where we have capabilities enabled, we have ways to communicate between different engineers and their roles, etc. Next slide, please. So I have kind of 3 final concluding slides here on benefits and some other kind of tips or things to take away. So some of these are already been highlighted earlier, but digital engineering expected benefits, informed decision-making, greater insight through increased transparency, especially that last example on the previous slide where you have access to information you didn't have access to before. As a program manager or decision maker, you have more information to make better decisions. This, towards that is also enhanced communication. It enables new communication pathways. It enables more efficient communication, those type of things as well. Increased understanding for greater flexibility and adaptability in design. I'll have a couple slides later. Sometimes we call this increased optioneering. You're able to test more options. You might have, you have greater access to data. That may mean you have greater access to potential solutions to the challenge that you have. You might have more reference points from previous designs to go from, those type of things. There's more information. The idea is at least that it will lead to this greater flexibility and adaptability in the overall design process. Increased confidence that the capability to perform is expected. You're bringing things together earlier. You're bringing things together before you have to build it all together and test it at that point. And failure at that point can be very expensive because then you have to go back and redo a lot of activities. So I even say this is increased confidence earlier in the design process that things will work and reducing risk in that overall picture. Finally, increased efficiency. Sorry. Yeah, increased efficiency in engineering and application practice as well. And I already really talked about that point in some of our examples in particular. But yeah, and overall, we enabling these pathways just facilitates someone can do more in their role with the capability being enabled to them. It's not more iterations between groups, things like that. Next slide, please. So some additional key points. This is fundamental engineering principles still prevail. This is not saying go do something radically different necessarily, but rather digital engineering type of ideas are taking good sound engineering judgment and enhancing them through these technology pathways, making the job easier, making standardization, reduce ideas. Those are more broad ideas. It's not a potentially a new way to do the engineering, but rather an improvement on existing good practice. A lot of data is key. So data capture and manipulation is essential and requires a digitally savvy engineer in general. This is a very data-centric type of approach to things. Also can be considered model-centric approach to things, and making sure that that is what's that is kind of the main deliverable or main source of communication rather than PowerPoint presentation or some other derived form from the data. Having the data available and the ability for anyone or the manipulation as needed is a part of this overall digital engineering vision. So digital evolution. I mentioned some tools. The tools continue to change over time. This is one space where there's still, I think, a lot of development work and standards and in tools and tool vendors and you understanding how you fit into a digital engineering picture or how your organization fits into that picture. So keeping up with it, having some eyes on what is going on can be quite useful to ensure that you are up to date on modern practice in this space. And then collaborative practices reborn. We talked about that in the previous slide. Those additional pathways are enabled. And then improved optioneering, enabling new, more efficient ways to generate multiple design options and evaluate them. Doing engineering design in this digital engineering way with digital threads means you can pull information more directly to evaluate those options in a more accurate way, in more with more candidates of what you might be considering. This optioneering idea, especially earlier in the design stage rather than waiting until things are fully developed, is another key point. And on the slide, I'll quickly go these. We're close to time. Keeping up with digital evolution. So learn how to code, learn how to use the tools. So in general, depending on your role, there might be certain tools that you need to know. But if you want to be, considered a strong digital engineer, fluency, at least in some form, whether it's interpreting what you're seeing from the tools or directly utilizing the tools. If you want to be able to actually manipulate the data that's being enabled through digital engineering, it might require some coding. So just keeping those things in mind. Soft skills still matter. This is using we're digital and automating pathways, but someone still needs to understand, communicate. Not everyone might be on the same page of how the digital engineering fits together. So having these effective communication skills and thinking and being effective through these new collaboration pathways is a soft skill that is important to keep in mind as well. And the final one is that various background skills are important. This is something that is meant to revolutionize the entire way the enterprise does their engineering efforts. Well, there's going to be pushback. So ensuring that different kinds of expertise, specializations, backgrounds are all considered. If someone isn't going to use the capability that you enable through digital engineering, then the impacts can be pretty minimal. So this idea of we talk about stakeholders in system engineering. There's a lot of stakeholders, most people in the digital engineering space, because a true digital thread would touch on what everyone is doing. So With that, I think, Andy, you're going to summarize just some of our quick.
You can do it.
Sure. Yeah, so we have, classes, we have different efforts, we have courses that I teach in model-based system engineering at CSU. We are doing work in digital twinning, in digital engineering. We have up and coming courses, and we didn't really talk about this too much in the presentation, but part of this is when you have data available and we have new technologies that enable us to look at, manipulate the data in new ways, things like augmented reality, virtual reality environments and classes, which will be supporting. Is that offered next fall? We supported very soon that we'll have more classes in that, which will be very exciting to see, and then different security collaborations, things like that as well. So I think we have more than we just listed here as well.
Yeah,
A lot of our
we do.
courses are aligned with the digital engineering vision in some way. I think that's what we have, and we're very close to time, so thanks everyone.